after defining the Zariski topology on an affine variety X in the last video, now we move towards the goal of using this topology to study X in different respects. And this following section is about using the topology to decompose any affine variety X into simpler or more fundamental pieces, writing X as a union of a finite set of affine varieties. And as an example, to give you an idea, you can look inside A2, affine 2 space, consider the following two affine varieties. One is the vanishing locus of xy minus x to the 3, and one is the vanishing locus of x squared minus 3x plus 2. So if you think about it for a second, what you can do with these equations is you can factor them. They're actually, as polynomials, they're not irreducible, but they're products of smaller factors. So here you see for this polynomial, you can draw out a factor x, and then you get this representation. And we have already seen that the vanishing locus of a product of ideals is the union of the corresponding vanishing loci. And so indeed, we get here that this vanishing locus is the union of the locus where y minus x squared is 0. So this is just the graph of the function x maps to x squared, something like this. And the locus where x is 0, which is just this. And again, here I draw the real picture to give you something to look at, but this works over any field. So what we see here for this x is that even though it's described by a single equation, it actually decomposes as a union of two pieces, which are in a certain sense simpler than the full space X. And here the story looks very similar. Here is actually just a single variable, and then you can decompose it as a product here. And you see then this space Y is just the union of the locus where X is equal to 1 and the locus where X is equal to 2, which are two lines like this. In both cases, we see that we represent our affine variety as a union of other affine varieties. But there is one difference, namely these two varieties, in this case here, they meet in a point, whereas here, the varieties are really disjoint. And so as a result, if you look at X, we think that probably this is a connected space. Certainly this picture here is connected. You can walk from any point to any other point like this. And it is connected, but it is still a union of affine varieties, whereas this looks disconnected. And the components, the connected components of Y should be these two things. And one thing we observe in this particular case is that these decompositions here came from the algebra side as factorizations of the polynomials describing these loci or of their respective ideals. Okay. So this was the example to keep in mind, the two different ways in which space can decompose as a union. And now we make this precise with the following definition. And this definition actually makes sense for any topological space. And we will apply it when X is an affine variety with the Zariski topology. So, but if X is any topological space, we can say that X is reducible if it can be written as a union, X1 union X2, where X1 and X2 are closed subsets, which are proper subsets of X. So they are they're not equal to X because, I mean, if you can take one of them to be all of X, then this is trivially true. You can take X is equal to X union the empty set. So here it's really important. These are proper inclusions. And if something is not reducible, it cannot be reduced into smaller parts, then we call it irreducible. And the second definition is very similar in this regard. We say that X is disconnected if it can be written as such a union of two proper subsets closed in X. And now we also require that their intersection is empty. That's a stronger condition. And if this is not satisfied, if X is not disconnected, then we call it connected. One hint here is that, I mean, this is a perfectly fine formulation. How you can also say it is that X is reducible if whenever X is the union of two closed sets, then one of them has to be X itself. That's an equivalent formulation. And if you do some of the exercises, you will see this is often more useful way to phrase things. Okay. But in any case, one immediate observation is that the condition of disconnected is just strictly stronger than of reducible because it just has this extra part here. And so in particular, if something is disconnected, it's also reducible. And taking the negation on both sides, it means that if something is irreducible, then it is also connected. Just as a small remark. And then in the example above, we had these kind of two illustrations. And what we can check is that both X and Y are reducible because they're unions of closed subsets, which are not everything. And in the case of Y, we can take these two closed subsets actually to have empty intersection. Y1 and Y2 don't intersect. And so Y is also disconnected. What is a bit more tricky to see, or where you need a slightly more argument, is that X is indeed connected. So here you cannot, I mean, it's clear that X1 and X2 would not give you an example for this disconnected definition because they actually intersect in this point. And it's a bit more tricky, or you need to put some more work in to show that in fact there's no such decomposition into two closed proper sets, which are disjoint. And then another thing to show about this new definition is that like all of these four pieces here, X1, X2, Y1, Y2, are irreducible. So they can no longer be decomposed further as above. And this, we're going to slowly work on this during the next videos. One remark is that intuitively, you would hope that a very simple affine variety, like for example, just A1, this should be irreducible. It shouldn't be decomposable into smaller things. And for A1, we have very good control over what the closed subsets are. They're either A1 itself or a finite set. And using this, it's a short exercise to show that A1 is indeed irreducible. We're going to see this kind of more in a more principled way, in more generality later. And it is true for this Zariski topology where the closed subsets are either A1 or the finite sets. But for example, if you take one of the more usual topologies, for example, of the complex numbers, A1 over C is just the complex numbers. If you put in the classical or Euclidean topology, then it turns out this is reducible. And it's reducible for a kind of stupid reason, because you can take C to be the union of this locus where the absolute value of X is less or equal to 1. This is a closed ball around the origin. Union, well, basically the complement of the open ball of radius 1. So everything, kind of everything except for a ball. And these are two closed subsets in the Euclidean topology. They're proper, they're not everything. And so because of this decomposition, C is reducible. And so even though this looks like a single piece, if you actually look at the Euclidean topology, it can be decomposed. And so this notion of being reducible or irreducible is not super useful in the classical topologies, but it will be very useful for the Zariski topology. One reason and one kind of nice feature of irreducible spaces, which is one reason why the notion of irreducible is so important, is that open sets in there are actually really big. And this is in the following way. So if X is an irreducible topological space, you can show that any two non-empty open subsets have non-empty intersection, which, I mean, is certainly not true for something with C. If you just take two open balls which are far apart, they have empty intersection. But in such irreducible spaces, whenever you have two open subsets which have at least one point, then they also have at least one point in common. And the second property is that any non-empty open subset in X is actually dense, which means its closure, the smallest closed set containing it, is everything. And I encourage you to try this exercise yourself, because, for example, A is basically just a reformulation of the definition of being irreducible. And then B also follows from very basic topology manipulations. If you want to see the solution, you can also look at Gutmann's script. It explains the argument in this remark. So in this video, we saw both the definition of irreducible and disconnected, and connected and reducible. And in the next videos, we're going to apply this really to the concrete example of affine varieties.